So, who wants to go away into the weekend having just received a brand new, wonderful, enjoyable, invigorating, informative math lesson? Not you? I'm sorry, guys. You know I really do love you, but I hate to give you a new math lesson right before the weekend. At least you'll have homework to do. Could be worse, right? But I am giving you a new math lesson before we go on our frolicking, fun weekend, our beautiful 3-day weekend that we enjoy every week so much. And the reason for that is we are just simply out of free days, really, with all the time off we've had for the weather, and unfortunately then for sickness as well. So we just have to make use of every time that we do have. And so we're going to move into our new chapter, chapter 11. And yes, guys and girls, I think this is a lot of fun. I hope you do by the time it's all said and done. And I know you guys, as smart as you are and as hard as you're working on things, I have a feeling that you're going to do well with it. Just give it a little bit of time and attention, and everything, as always, is going to be just fine. So what we're going to do in our first lesson, section 1 of chapter 11, is we're going to be expressing roots, okay? Expressing roots. And we've dealt some with square roots. We even have some cubes, but we're going to deal more with cube roots. We're going to be talking about radicals in chapter 11, which is where you have a root symbol. And a lot of times you're going to be taking a square root. Other times you'll be taking a cubed root, and still more times, as we'll see in this lesson where we're right over here, the root of 4, the root of 5, and no, it's not the root of all evil. That's money. You're confusing that. Now, these roots, I think they're pretty cool, and hopefully we'll find some degree of enjoyment out of them, even though it might not be the first thing that we would pick to do on a Thursday before we head out for the weekend. Okay, before we get into all of this, though, to understand, and this is going to be some review to you, but stay with me. I want to make sure we're all on the same page, and then I assure you very quickly, it will not be review for any of us. But to understand what a square root means, you first really need to know what a square is. For instance, 3 squared, and remember that's not 3 times 2, rather that's 3 times itself, which is 3. 3 times 3 is 9. Why is that significant in relation to square roots? Because the square root of 9 is 3. And the reason for that is, what number times itself gets you back to that original number underneath that square root symbol? And that number is 3, because 3 times 3 is 9, therefore the square root of 9 is 3. But you see the corollary between these two? Guys, as addition is to subtraction in algebra, and as multiplication is to division, and with both of those vice versa, so also the square root is to the square, and vice versa. They are inverses or opposites of one another. And so if you understand one, it can help you to understand the other. Well, that's also true with cube roots. To really get a full meaning of what a cube root is, or any root for that matter, we first need to understand what a cube, or what that root would be as an exponent for that term, and in this case it's a number. 3 cubed, okay, is not 9. That's 3 squared. In other words, it's not 3 times 3, which would be 9, but it's 3 to the 3rd power, meaning it's 3 times 3 times 3. 3 times 3 is 9, and 9 times 3 is 27. And so the cube of 3, or 3 cubed, 3 to the 3rd power, is 27. Now, have you seen these and have you dealt with these yet? Cube roots. It's the inverse, or it's the opposite of a cube. So if I have the cube root, and by the way, if you have this, what looks like a division symbol, but by this point we know it's not, it's a square root symbol. But if you have this square root symbol and there's no number there, it's always implied that there's a 2 there, meaning you're taking the square root. Now if you have a different number, like a 3, that means you're taking the cube root. And you can have any number there, as we see 4, as we see 5, okay? But in this case, it's a 3. What's the cubed root of 27? The cubed root of 27 is 3, and here's why. What number times itself a second time, as opposed to just to the once with the square? times itself twice, 2 new times, gets you to 27. Well, that number is 3, because 3 times 3 is 9, and 9 times 3 is 27. So I hope that adds up. I think it does. You know, we've dealt some with similar types of things, and certainly a lot with squares, and I think even some with square roots, and we've certainly dealt with cubes, and even larger than that. Well, when we're dealing with the roots, square roots, cube roots, or whatever roots to the nth term, it's just the opposite of that number having that same number as an exponent. So here are 2 important terms too. Whatever that number is, okay, whatever type of root as the reverse of an exponent is being taken out of a number, that is called the index. That's the index. Now the number that's under the roots, whether squared, cube, or anything else, that's under the root symbol, that's called the radicand. Radicand. And the reason for that is because it is properly understood mathematically as a radical. A radical, which is our whole chapter, what it's going to be on. Okay, so having gone through that, let's just breeze through, for the most part, these right up here. And even these won't be too bad, and then we'll concentrate a little bit more on those later on. 1a, what is the square root of 2? Do we really even need to go through this part? Carter right now is like, dude, you kidding me? Come on. Okay. And Caden and Micaiah and Anna and probably too, Mike and Andolin, and am I leaving any of you guys out? I hope not. I'm naming all those names. No, Parker. Parker, you're unforgettable. How could I forget you for a half second? So, now, we know that that's so easy. The square root of 4. What times itself gives me the number 4? Dum, idiot. 2 times 2 is 4, so the square root of 4 is 2. Okay, let's move on to more complex matters. This isn't that much more complex, however it is slightly more so. What's the square root of 16? What number times itself gets me to 16? That is the number 4. The number 4. Therefore, the square root of 16 is 4. However, look, this is different. There's a negative symbol to the outside. Once you simplify the inside, you just apply that. And don't let me confuse you by this, okay? But it can maybe be a little bit important for later on. It's one of those situations where there's actually, between that negative sign, kind of like a parentheses. Why would I do that? That's terrible. Let me just rewrite the whole thing now that I thoroughly embarrassed myself. I'm going to rewrite out here a little bit more to give me some more space. That's a negative sign. Well, it's like if it's outside of a parentheses, a negative sign, there's actually an imaginary understood 1 that's between that negative sign and that, and it's being multiplied to it, and it's a negative 1, even though we don't write it in because it's understood, okay? So whenever we simplify square root of 16, which is 4, then we multiply it. And once again, there's an invisible multiplication sign. We multiply the 4 times negative 1. And so it's not just a 4, but it's a negative 4 because the negative is found outside of the square root symbol. 2a, slightly el differento. On 2a, we're dealing with a cubed root. Okay, what's the cubed root of 125? In other words, what number times itself gets me to the number 125? Well, we know from our practice one that we did right up here, we do know from that the cube, the cube, no, that's where I'm going. We're good, but we can do it that way too. But the cubed root of 27, we know is 3, so the converse of that's where I was going, is a step ahead of myself. 3 to the 3rd power is 27. Well, let me show you something, okay, on my calculator. Can you see that? I think you can see that okay. Let me show you something on my calculator. Guys, I don't care if you use your calculator sum for this, okay? I'll show you later on. There'll be some things you can't really use for them to help you that much, but to get some helpful hints until we get these down better, that's okay. What is, I could do 4 to the 3rd power, or just do it manually, which is probably faster in this situation. But 4 times 4 times 4 is what? It's the number 64. So that's not 125. Okay. Well, how about if I have 5 times 5 times 5, or 5 cubed, in other words. Aha! Eureka! I found something, didn't I? 125. So, if 5 times 5 times 5 is 125, guys, necessary converse, inverse if you prefer, opposite of that, what number times itself gives me 125? That number is 5. And so therefore the cube root of 125 is just simply 5. That's not bad, is it? How about this one on 2b? 2b is, what is the, how would you even say this? The quattro, we're doing Spanish math maybe? What's the quattro root? What is the quad root maybe? I don't know. What's the root of 4? We'll call it that. Of the number though, 81. Okay, I'll try to get this once again where you can see it and it's not all wavy and will have to make you sick. Okay, let's just punch something in. What times itself times itself times itself, so it has an appearance of 4 times. Oh, here we go. 4 times. Can you see that total? To get us to 81. Well, let's just punch a few things in our calculator. How about 2 times 2 times 2 times 2? So I have 4 total appearances, which is what I need. And look, that's the number 16. That's not nearly big enough. Let's try 3. Guys, when you're dealing with exponential matters, they can exponentially multiply. So don't think you need to start with a huge number when you're multiplying a number by itself 3 times. Okay, to get to 81. Don't think you have to start with a big number. Let's try 3 times 3 times 3 times 3. 4 times total appearances. Look at that. 81. And so since 3 times itself, okay, you have the number and then times itself 3 times, so a total of 4 appearances is 81. What number times itself times itself times itself is 81? Well, it's simply the number 3. Again, please use your calculator some in this, all right? Don't absolutely kill yourselves on really just silly things. 3a, what is the square root of negative 4? Okay, the square root of 4 is what? What number times itself gets us to 4? That is the number dos, okay? It's the number 2, but then I would just apply the negative sign, right? Not so fast. Guys, this is a different expression than this. Negative square root of 16 is different than the square root of negative 16, or in this case, negative 4. Think about it. What number times itself gives you a negative number? The answer to that is no number at all. Think about it. If you start out with a positive number and you multiply it by itself another positive number, it has to be a positive number. If you start out with a negative number and you multiply it by itself another negative number, what do 2 negative numbers always make? A positive number when they're multiplied together. And so there is no number that you can take the square root of it, all right, and it be a negative number underneath and come out with a correct answer. It's mathematically impossible. So how would I answer that? I wouldn't say 0. I would put a 0 and draw a line through it, circle it, which means, as we've done a lot, there is no solution to that problem. 3b looks the same, but it's different. Look, there's a negative number, but it's underneath a cube root. Is it possible to multiply a number by itself twice, so that when it's all said and done, you have 3 multipliers, a total of 3 multipliers that are negative, and you still get a negative answer? Yes. Because remember the rule, if you multiply negative numbers an even amount of times, no matter if it's like 1,000,004 times, because 1,000,004 is an even number, you're going to have a positive number, even though you're using negative multipliers. If you multiply anything an odd number of times, say even up to 1,000,005 times, because 1,000,005 is an odd number, you're still going to have a negative number, okay, because you have a negative number of negative multipliers. So if that is correlating, then if I have the cube root of a negative number, that's okay. If I have the root to the 5th power, that's okay for a negative number too, because you can have a negative number as long as it's an odd number of times. But this is understood. If there's nothing written, it's squared, and you can't have a negative number an even amount of times. And on this one, 4, if this would have been negative, the square root of negative 81 wouldn't have worked, because you would have to have a positive number under there because of the even number of times it's being multiplied, or the number of multipliers there are. Okay? Now, if I'd have had a negative outside of here, like the negative outside of the 16, that's a whole different ballgame. It's not applied underneath the square root or cubed root or whatever root symbol, so that's okay. But underneath it, an even number of times is never okay. That's no solution. Now, this one's okay. We can do this one. The cube root of negative 27 over 125. I'm going to show you guys a cool shortcut rule, and you might know this already, but you can rewrite this cubed root of one whole number as a fraction. You can rewrite it as two different fractions and two different square root symbols. And what I mean is this. You can rewrite it as the cubed root of 27. I want to make sure to put that 3, because otherwise I'm insinuating it's a square, and it's not. Or I'm sorry, a square root. It's a cubed root. I can do the cubed root of 27 over, and notice how they're separated now and not all under the same dry umbrella. I'm going to do cubed root of 125. And here's the reason I did that on this one, separating them. Guys, is 27 a perfect cube? The answer is yes, because what times itself gets you to 27. You see, I can just simplify that cubed root of 27 to 9. That's why I broke it up. And I can put that over, is 125 a perfect cube? I just did that, and you just did that right up here in 2a. What's the cube root of 125? 5. Because 5 times 5 times 5 gets you to 125, right? So, right up, you guys probably already caught that, sorry. I told you, I record these late at night. It's late. I don't even know what time it is right now. It's probably, give or take, 11 o'clock. And that is obviously not 9. The cube root of 27. 3 times 3 is 9. Times 3 is 27. I probably stopped short in my brain. So the cubed root of 27, what times itself equals 27 is 3. Does that look a little bit better? Thank you for your generous forgiveness. So the cubed root of 27 is 3. The cubed root of 125 is 5. And so look, I have a simplified answer with no cube roots, no roots of any kind at all. That looks a lot better, doesn't it? 3/5. But the reason I did that is because I broke it up. If I'd have just tried to reduce this within that cubed root, I'd have had a real mess on my hands. But breaking it up like that makes it so much easier to do. Okay, how about for C? This is the largest one in terms of roots that we've done so far. It's a root of 5. And the number is negative 32. Now remember, when you multiply things by each other, those are my kids' toys, by the way. Remember, I'm in the playroom right now. You can't see it, but this place is a mess. Maybe I'll show it to you eventually. It looks great though when you only have focus on the board. Let's just try to keep it that way. So on 3C, remember, you'd think, well, I need a pretty big number to get to 32. Not when you're multiplying it by itself 5 times. I'd start small. It's an even number. Okay, so let's do that. Let's start with an even number, if I can get this reasonably situated here. So it doesn't make you sick looking at it. How about 2 times, and I could just do to the 5th power if you have that caret. I do, but I'm just going to do it this simple way. 2 times 2 times 2 times 2 times 2. Whoop, not 5. 2. 2 times 2 times 2 times 2. Do I need one more times 2? I know the calculator's right. Look at that. 32. And so what times itself, okay, a total of 5 times is multipliers. What number times itself, times itself, times itself, times itself gets you to 32? That is the number 2. But notice that that's a negative 32. And that's okay because it's an odd number. If it were an even number like 2 that's implied, or 4 that's written, or 6, or 1,000,004, it wouldn't work. If it were all the way up to 1,000,005, it would work because that's odd. As long as it's odd, you can have a negative underneath the root symbol. But if it's even, you can never do so. So what times itself, times itself, times itself, times itself gets you to negative 32. That number is negative 2. So I think we're doing all right so far, don't you? Not too bad. Let's move on to number 4. Let's do the square root of 129. And what we're going to do here is just mentally estimate. Mentally estimate the square root of 129 to the nearest integer. Then use a calculator to find the square root of 129 to the nearest hundredth. Okay, so we're just going to round it to the nearest whole number. Square root. Now 129 is obviously not a perfect square, else we wouldn't be estimating and then using a calculator, because it's not really that large of a number. It still fits in the multiplication table as a product. Okay, 129. Let's go smaller. What number times itself gets us around that ballpark from the multiplication chart? What is 11 times 11? Does anybody know that one? Can you tell me what that is? 11, think about it just a minute. What is 11 times 11? 11 times 11 is 121. Okay? Now that's the square. Okay, well, let's just say 121 for right now. Alright, that's to the left. Over here to the right, what's a bigger one than that? Well, we'll just go up one. 12. What's 12 times 12? 12 times 12 is 144. So 11 times 11 is 121. 12 times 12 is 144. Now if I were to take the square root of those two numbers, what number is going to fit right in the middle right there? That's this number. 129 goes between 121 and 144. So that tells me that this number, which I know 121 is 11, the square root, I'm sorry, 121 is 11. And I know the square root of 144 is 12 because 11 times 11 is 121, 12 times 12 is 144. Then the square root of 129, which is between those two numbers, has to be between the numbers 11 and 12. But to which of these numbers is it closer? Okay, 121 is 8 spots, 8 units away from 129. 144 is what? 15 spots away. So what's closer, 8 or 15? Only 8 spots away is closer. And so our nearest number, nearest integer, is going to be the number 11. Okay? Now, what I'm going to do is what the instructions told me. Let me get my calculator back here where you can reasonably see it. And I'm going to take the square root, which is right here, of the number 129. Oh, gotta put my 9 in there. Okay, 129. Now we're back in business. Square root of 129 is 11 point a whole bunch of numbers, but it said to round it, wasn't it, to the nearest tenth? And so the nearest tenth is going to be 11 points. What do we do with that 5? Bring that 3 up. And so we're going to have 11.4. So I have two answers there. The first one's my rounding it to the nearest integer. My second one was using my calculator to get it to the nearest. I said tenth, actually it's the nearest hundredth. And that's 357. So we use the 7 to round up the 5. Let me fix that really quickly, okay? Not a big deal, but I want to do what I said from the get-go. So it's going to be 11.36, if that's the case. Okay, we round it to the nearest hundred. We're getting really exact right there. That's not hard. That's pretty fun, too. Number 5, we are going to round the cubed root of 50 to the nearest integer. Let's round the cubed root of 50 to the nearest integer, and then we will use a calculator to find it to the nearest thousand. So remind me, talk out loud, Mike, talk out loud, Micaiah, and I'll hear you maybe through the camera one day later, or maybe a couple, who knows where we are right now, day-wise, you and me both. So, Cubed root of 50. Well, we do know this. We know that the cubed root of 27 is a perfect cube. Okay, we'll go to a whole number. So let's try that one. The cubed root, I need to write that 3 in there to differentiate between a square root and a cubed root. Square root of 27, I know is 3. I'm going to use that. What's the next one up from 3? 4. What is 4 times 4 times 4? 4 times 4 is 16. 16 times 4 is 64. And so the cubed root of 64, I need to make sure I write that 3 for my cube. Okay, so obviously 50 is going to fit between these two numbers. This number's 3, that number's 4. To which number is 50 closer? Is 50 closer to 27? What's the difference between the two? 23 spots. That's sizable. 50 and 64, how many spots between? Only 14. 23 units, 14 units. 14 units is closer. Therefore, in my just ballpark mental estimation, 4 is going to be correct. But now what I need to do in my calculator, I've been given instructions, is that I need to, decent spot, okay. We need to take the square root, no, messed up, didn't I? Need to take, stop it, I don't like you either. We need to take the cubed root, right there, third time's a charm for the cubed root, right? Sorry, I'm operating where I'm not looking straight on, it's hard to punch the right button. Okay, the cubed root, now we're in business again, of 50, which equals, to the 1,000 spot, which is 3 places, 3.684. Okay, 3.684. Looky there. Shannon Clark just posted in Miss Nicole and Mr. Derek's 7th through 9th grade class. You might have seen my Facebook update. All right, so 3.684. Attention span of a field mouse. That is I. Using a calculator to the nearest hundred, 3.684 for the 1,000th time. We rounded to the 1,000th place. There we go. All right, you might look at that and say, well, wait a minute. I thought we said it's 4 and not 3 in our estimation. Well, remember, we were rounding, and we were correct in that rounding. If you were to round from 0.6, you go up to 4 and not down to 3. But that's a more exact answer, and we've done it both ways that we've been requested. Mentally, ballpark, exactly, calculator. So let's do numbers 6 and 7. Now for that, we need to have some quick discussion. Let's talk just a little bit, heart to heart, right here. Heart to heart, brain to brain. Okay, ready? Make sure you get this down. This is brand new stuff. This is really, really neat too. X with a power that's a fraction. And that fraction here, we're expressing it as giving more variables. A over B, okay? X to the A over B power is what that is. That's an exponential form. That's in exponential form, okay? If I want to turn that into radical form, I can, and here's how. Check this out. The number or term itself, I put under the root, whether that's square, cube, or whatever, okay? I put that as the term under the root, the term itself. I move the denominator in the power out to the spot of whether that's going to be a square, a cube, or whatever number that is. I move it out to the root power spot, the denominator. And the numerator of the power, I keep attached, standalone, underneath that root to the term itself. Does that make sense? So my term itself is going to go under the root, and whatever the power of that root is going to be is the denominator of the power in exponential form, and then the numerator of that power is going to move just attached to the term itself under the root symbol. Okay, and then over here is basically it's the same. You know how you can write powers in different ways, and that's the same case with that, but it's the same thing as this. I'll let you look at that. You can have in parentheses the b root, just as whatever number that's going to be, over the term x, all that in parentheses, and then the power a from the numerator can be out, but it's the same thing as this. Now, let's put it in numbers form where it makes a little more sense to us. If I had 8 to the 2/3 power, sounds funny, doesn't it? Looks funny too. 8 to the 2/3 power, what I do is I keep the term, the whole number, and put it under the root symbol. I take the denominator and I put that as the root power, which in this case is going to become a cube because the denominator is a 3. And I move the numerator to the exponent of the term of which the root's being taken. And since I have 8 to the 2/3 power, my denominator is going to become the root power, and my numerator is going to become the new standalone power of the term under that root symbol. And again, I can rewrite it in this way. It's the same thing, just a rearranging of powers, which we've done before. But the way I'm not going to write it like that. I just show you that because you might see it on a quiz, or you might see it on a test that way. And I want you to be prepared and not be like, oh, wait a minute. You'll know what's coming, okay, whenever you see it that way. So let's do 6a, and let's turn 5, and I should have that a little higher, sorry about that. But that 2/3, it's not 5 and 2/3 is a mixed number, but it's 5 to the 2/3 power. I got a little big with those numbers, that's my bad there. But 5 to the 2/3 power, we're taking it from exponential and we're turning it into radical form, okay? How do I do that? I take the number itself, in this case it is, or it can be a term, which we'll do that some. I take the main term, the big thing, okay, itself, I do a root symbol, and I move whatever that term is, and if it's a number, that's great, a big number. In this case, it's a 5, and that's going to be my big number under the root symbol. I take the denominator, which is a 3, and I turn that into, remember our terminology, my index, which is the number kind of in the crook of the V, okay? And that means it's going to be a cubed root in this instance because the denominator is a 3. And then I take my numerator and I simply apply that as my new standalone exponent that's attached to my term. And so I have the cube root of 5 squared. I can simplify that. And the reason for that is I know what 5 squared is. It's 5 times 5. And you know what 5 times 5 is. And so it's the same thing as the cubed root of 25. Now I can't simplify it any further than that because 25 isn't a perfect cube and there's no perfect cube numbers into which I can break it down, but I can simplify it to that. So, does that register? Does that seem okay? That's pretty cool stuff, isn't it? These get really fun. Okay, and I know we're running out of time, so I don't want to take up too much of the rest of your day. Let's get this finished. We have a root into the 5th power, okay, to the root to the 5th power, and our radicand terminology is the term that is underneath that root symbol. And what I want to do is take this in radical form and turn it into exponential form, which is the opposite of what we did right here. So how is it that I do that? Well, this is even simpler in my estimation. We'll see if you think so. I keep the term itself, whether it's under the radicand or whether it is the radicand, meaning under the root symbol, or it's an exponential form. I keep the term, the main term, which is x. But look what I do with this. This used to be, or if not, I can turn it into the power under the root symbol. I can turn that into my numerator in my exponent, and whatever the power is as the root to the outside, look, that's my denominator. Whenever the exponent under the root is my numerator, the root power is my denominator when I turn it into exponential form. And so the 3 is going to be on top as a power, and the 5 out here is going to be on the bottom as a power. So it's x to the 3/5 power. I like that, don't you? That's some fun stuff. So 7a, let's get just a little more complicated, guys. As we finish, I'm going to erase this over here. You okay with that? Good. I feel like I just got, how many do we have in there? 7, right? I feel like I just got 7 confirmations. Okay, move over here so I have more space. I have 3, got better? Big, right? 3 1/2 x 3/4, okay? That's an exponential form, and I need to express this, I am being told, as a single radical. Here's the way I have to do that. I have to turn these into like denominators. And so I have to do something with that 1/2 that's my exponent of my 3. What do I do to turn it into the same denominator as this power over here to my x term, which is a 4? How do I turn the 2 into a 4? I multiply not just the bottom, but also the top by 2. Okay? And the reason for that is 1 times 2 and 2 times 2. That gets me to 3, and as a power, 2/4. And I just rewrite x and 3/4. Guys, here, now I'm not going to add and subtract these, okay? Like we do with fractions a lot. And the reason these are being multiplied together, but here's the reason I did that. I have to have a common denominator before I can move that denominator as a power out to the root power. Remember, that's what I do with the denominator. I move it to the root power. And so now I have a common one. I can make that root power 4. But I couldn't do that when they were different denominators. All right? Now, what do I do from that point? I just rewrite now underneath my main terms, but with my new standalone powers, which is 3 squared times x cubed. I just keep the numerators as the powers. I can simplify that, can't I? And here's how. I'm going to keep my quattro, we call it, my Espanol quattro root, as we're doing Spanish math. What is 3 squared? 3 times 3 is 9. And then I just have remaining x cubed. I would like to say once more, isn't that neat? And isn't that fun? Our answer, simplified, is the root to the 4th power of 9x cubed. Okay, so let's do this final one, and once again I'll blow it up. And what we have down here is we have a root to the 4th power of 7x, 7x cubed. Gets hard to say after a while. Y squared. And so I'm going to rewrite 4, because my power, and 7x cubed y squared. What I'm trying to do with that radical, guys, is turn it into exponential form. How do I do that? Well, all I do is keep my same base terms, okay? 7. Now this one's tricky. Look, 7 has a power even though we don't write it. What is every number or every variable understood to be in terms of to a power if we don't see it? That is 7 to the 1st power, because 7 to the 1st power is 7. And so what I'm going to do is I'm going to keep as a numerator what's a standalone power under the root to move it out, but I have to include the root power out here as my denominator. See, I'm working in reverse order to what I just did. I'm going to keep my base of x. All right, I'm going to keep that 3 that's a standalone attached to it, but to move it out from under that root symbol, I have to apply the root exponent out here as the denominator. So I have 7 to the 1/4 power, x to the 3/4 power, and so what am I going to have is I keep y as my base in terms of a power. The standalone exponent becomes the numerator, and what does the root power become? The denominator. And so I have y to the 2/4 power. I'm almost done, but I need to simplify a little more to be entirely correct. I went my water bottle, just like in school. Your guys' stinking water jugs flying, exploding all over the place. 7 I keep. 1/4, can't do anything with that. X, 3/4, can't do anything with that. The reason I'm rewriting, guys, what can I do with 2/4 as my y exponent? That can reduce to what? When writing an exponential form, make sure that they're reduced to the lowest power. Now the reason it's a power that's not in the lowest number is because it was in radical form, and you would transform it back, getting a common denominator if you went that direction, but we're going the opposite direction. And so we reduce the lowest terms, and all of our denominators in so doing are not going to be the same. And so those are my two answers on number 7, 7A and 7B. Okay, that's all that I have. I know that's a little bit of a challenging math lesson as we head out for the weekend, but thanks for being patient. Thank you for understanding. And guys, there's light at the end of the tunnel. We are almost there. The school year's almost done, and there aren't many more sections and many more chapters to be learning. But I'm proud of you, and I appreciate every one of you. And I might even say, I love you. I at least strongly like you. Most of you anyway. No, I love every one of you. You're special kids, and I really do appreciate all the work that you put in, and I mean it. It's absolutely showing. Okay, guys, have a great weekend, I'd say, and I will see you, the good Lord willing, on Monday. Adios, amigos.